In January 2020, the gravitational wave detectors LIGO and Virgo picked up a signal. The signal lasted a fraction of a second. It was a ripple in the fabric of spacetime itself, a distortion so small that it moved the mirrors of the detector by less than 1/10,000th the width of a proton. But the instruments were sensitive enough to catch it, and the data was clear enough to analyze. And what the analysis showed was that approximately 910 million light-years from Earth, a black hole and a neutron star had found each other, spiraled together, and merged. The event was catalogued as GW2-00105. It was the first confirmed detection of a mixed merger, a black hole consuming a neutron star, in the history of gravitational wave astronomy. It was celebrated as a landmark detection. The analysis was published. The masses of the two objects were calculated. The properties of the merger were characterized. The scientific community moved on. Nobody questioned the assumption baked into every calculation. On March 11, 2026, a team from the University of Birmingham, the Universidad Autónoma de Madrid, and the Max Planck Institute for Gravitational Physics published a new analysis of the same signal. They had gone back to GW200105 with a different model, one that did not make the assumption every previous analysis had made. And what they found in the data, when they removed that assumption, changed everything about what GW200105 had been telling us. The orbit was oval. Not slightly oval, not marginally eccentric. Oval enough that a circular orbit could be ruled out with 99.5% confidence. Why oval? In a way that contradicts the most basic expectation of how black holes and neutron stars are supposed to behave in the moments before they collide. Oval in a way that no neutron star black hole merger had ever been observed to be before. The question that follows from that single shape is one of the most unsettling questions in modern astrophysics. If the orbit was oval, and if that oval orbit was the result of a chaotic formation history that no standard model predicted, how many other gravitational wave events were we wrong about for the same reason? To understand why the shape of an orbit matters this much, you first need to understand what a neutron star is, what a black hole is, and why the path they take toward each other carries the entire history of how they came to exist. A neutron star is what remains when a massive star, somewhere between 8 and 20 times the mass of the Sun, exhausts its nuclear fuel and dies. The outer layers of the star explode outward in a supernova, one of the most energetic events in the observable universe. What is left behind is the core, compressed by the violence of the explosion into an object of extraordinary density. Neutron stars are the densest objects in the universe that are not black holes. They are the boundary condition. Push a neutron star hard enough, add enough mass to overcome the quantum pressure of the neutrons, and it collapses into a black hole. A singularity, a point of infinite density from which not even light can escape. Black holes that form from collapsing stars typically contain between 3 and several tens of solar masses, depending on the mass of the original star and the specifics of the collapse. They are invisible by definition, but they bend space-time around them in ways that are measurable, and when they interact with other massive objects, they produce gravitational waves that propagate outward through space-time at the speed of light, carrying information about the masses and motions of the objects that produced them. When a black hole and a neutron star find each other and begin to orbit, they lose energy continuously by radiating gravitational waves. The energy loss causes the orbit to shrink. The orbit shrinks. The orbital period decreases. The objects spiral closer and closer together. The gravitational wave emission intensifies, and eventually the two objects merge in a final catastrophic collision that sends a burst of gravitational waves outward in every direction. This is the key to understanding why the oval orbit of GW2 00105 is so unexpected. When two massive objects orbit each other in an elliptical path, the gravitational wave emission they produce depends on their separation. When they are close together, moving fastest, they emit more gravitational wave energy. When they are far apart, moving slowest, they emit less. This asymmetry between emission at closest approach and emission at farthest separation causes the orbit to change shape over time. The ellipse becomes less eccentric. The oval becomes rounder. Given enough time and enough gravitational wave emission, any elliptical orbit will eventually circularize into something that looks nearly perfectly round. The timescale over which this happens depends on the masses of the objects and the size of the orbit. But for black hole and neutron star pairs detected by LIGO and Virgo, which have been radiating gravitational waves for millions or billions of years before the final merger, the theoretical expectation is that the circularization will be essentially complete long before the merger. By the time the two objects are close enough for their merger to produce a detectable gravitational wave signal, the orbit should be a circle to such precision that the deviation from circular is unmeasurably small. Every neutron star black hole merger detected before GW 200105 had been consistent with this expectation. Every signal showed circular orbits, and every model assumed circular orbits. The assumption was so well supported by theory and by every previous observation that when the original analysis of GW 200105 was conducted in 2020, circular orbit was simply the starting assumption. Nobody tested it. Nobody had a reason to. The 2026 analysis tested it. The result, ruling out a circular orbit with 99.5% confidence, means the assumption was wrong. The orbit was not circular. It had retained significant eccentricity all the way to the final moments before merger, in direct contradiction of the theoretical expectation that billions of years of gravitational wave emission should have circularized it completely. Something in the history of GW 200105 prevented the circularization process from completing. Something happened to this system that kept the orbit oval long after it should have been round. And the only mechanism that can do that is a mechanism the standard model of isolated binary evolution does not include. The clue is in the shape of the orbit itself. An isolated binary system, two massive objects that form together and have been orbiting each other in relative isolation for millions or billions of years, loses energy exclusively through gravitational wave emission. That energy loss circularizes the orbit smoothly and predictably. By the time of merger, the orbit is round. This is not just theoretical. It is what every observed merger before GW 200105 confirmed. If the binary system exists not in isolation, but in a dense stellar environment, a globular cluster or a galactic nucleus where many massive objects are packed into a small volume, gravitational interactions with neighboring stars or compact objects can perturb the orbit. A close encounter with a third massive object can stretch an orbit that was nearly circular back into an ellipse. Multiple such encounters can repeatedly re-eccentrify the orbit, even as gravitational wave emission works to circularize it. In a sufficiently dense environment, the eccentricity can be maintained or even increased all the way to merger. This is called dynamic formation. The binary does not form from two stars that were born together and evolved in isolation. Or it forms in a chaotic, dense environment where the gravitational interactions of many bodies can bring two compact objects together in ways that preserve eccentricity long after isolated binary evolution would have eliminated it. Geraint Pratton from the University of Birmingham stated it directly. The orbit gives the game away. Its elliptical shape just before merger shows this system did not evolve quietly in isolation, but was almost certainly shaped by gravitational interactions with other stars, or perhaps a third companion. The oval orbit is not just a surprising measurement, It is a confession. It tells us where GW2001105 was born. But the implications do not stop at the formation history of one merger event. Because when the 2026 analysis corrected the circular orbit assumption, it did not just find an oval orbit. It found that the masses of both objects had been calculated incorrectly in every previous analysis. When you assume a circular orbit and fit a theoretical model to the gravitational wave signal, the masses you extract are correct only if the circular assumption is correct. If the orbit was actually oval, the signal looks slightly different from what a circular model predicts. Fitting a circular model to an oval signal produces systematic errors in the extracted masses. The 2026 analysis found that the black hole in GW200105 had been underestimated. Previous analyses placed its mass at approximately 9 times the mass of the Sun. The corrected mass is approximately 13 times the mass of the Sun. The neutron star had been overestimated. The corrected mass is lower than previously calculated. These are not trivial corrections. The mass ratio between the black hole and the neutron star is one of the fundamental parameters that determines how a mixed merger evolves and what it produces. Getting it wrong means getting the physics of the merger wrong. And the only reason it was wrong was an assumption that nobody tested because nobody had a reason to question it. This raises a question that the research team does not fully answer, but that sits at the end of every paragraph of the paper, like a shadow. GW2001105 is not the only gravitational wave event that was analyzed with a circular orbit assumption. Every gravitational wave event ever detected was analyzed with a circular orbit assumption, because circular orbits were what theory predicted and what every observation had previously confirmed. If one event turns out to have had an oval orbit that invalidated the circular assumption, the question becomes how many others might have the same problem. The 2026 team analyzed GW200105 specifically because they had a new model capable of measuring eccentricity. Applying that model to every previously detected gravitational wave event has not yet been done at the scale and precision required to answer the question definitively. Some events will almost certainly confirm circular orbits because the circularization process really does work as theory predicts in most cases. But some events, perhaps more than one, perhaps more than a few, may turn out to be oval when examined without the circular assumption. How many gravitational wave events have we been reading with an assumption we never verified? How many mass measurements are systematically biased for the same reason the GW200105 measurements were biased? These are open questions. They are not comfortable ones. The standard model of how black hole and neutron star binaries form has two main pathways. The first is isolated binary evolution. Two massive stars are born together from the same molecular cloud. They evolve together, each exhausting its nuclear fuel and collapsing in sequence, producing first a neutron star and then a black hole from the same stellar pair. They spiral inward over billions of years through gravitational wave emission, the orbit circularizing as they go until they finally merge. The second pathway is dynamic capture. In a dense stellar environment, and two compact objects that did not form together encounter each other through gravitational interactions and become gravitationally bound. The orbit they settle into can be eccentric because it was formed by a chaotic interaction rather than a smooth evolutionary sequence. Subsequent encounters with other objects in the dense environment can maintain or increase the eccentricity. The binary formed this way looks different from an isolated binary in the orbital properties it retains all the way to merger. The standard expectation before the 2026 result was that the isolated binary pathway was the dominant formation channel for mixed mergers. Dynamic capture was considered rare. The population of mixed mergers detected by LIGO and Virgo was assumed assumed to be overwhelmingly from isolated binary evolution. GW200105 challenges that assumption directly. The oval orbit is a smoking gun signal of dynamic formation. It tells us that at least some mixed mergers come from the dynamic pathway. And if one of the first confirmed mixed merger detections in the history of gravitational wave astronomy came from the dynamic pathway, the question of how common dynamic formation actually is becomes urgent. Patricia Schmidt from the University of Birmingham put it plainly. This discovery gives us vital new clues about how these extreme objects come together. It tells us that our theoretical models are incomplete and raises fresh questions about where in the universe such systems are born. There is a historical parallel worth drawing here. In 1609, Johannes Kepler published his first two laws of planetary motion. The first law stated that planets orbit the Sun in ellipses, not circles. This was not a small correction to the prevailing model. The prevailing model, built on Aristotelian physics and Ptolemaic astronomy, required circular motion because circles were considered geometrically perfect. The parallel to GW200105 is not perfect. Planetary orbits are elliptical because of how gravity works in a two-body system, not because of dynamic interactions. But the broader principle is the same. An unexpected shape in an orbit carries information about the physics of the system that the assumed shape was hiding. Assuming circular orbits for mixed black hole neutron star mergers hid the dynamic formation history of GW200105 for 6 years. The Einstein Telescope, a proposed underground gravitational wave observatory in Europe with arms 10 kilometers long rather than the 4 kilometers of current LIGO detectors, will detect gravitational wave signals at signal-to-noise ratios so far above current capabilities that measuring orbital eccentricity will become routine rather than exceptional. The Cosmic Explorer, a proposed American next-generation detector with 40-kilometer arms, will have similar capabilities. Together, these instruments will detect not hundreds, but hundreds of thousands of gravitational wave events per year, with enough sensitivity to measure the orbital shape of every event rather than just the loudest ones. Gonzalo Moras from the Universidad Autónoma de Madrid stated it clearly. This is convincing proof that not all neutron star black hole pairs share the same origin. The eccentric orbit suggests a birthplace in an environment where many stars interact gravitationally. That birthplace, a dense stellar cluster or a galactic nucleus where the gravitational interactions of many massive objects shaped the orbit of a system we detected as a ripple in space-time 910 million light-years from Earth, is now part of the story of GW200105. It always was part of the story. We just could not read it until someone went back to the data and asked whether the orbit was really a circle. There is something worth sitting with at the end of this story. The 2026 analysis did not use new data. It used the same signal from January 2020 that had been sitting in the archives for 6 years. It did not have access to a better detector or a longer observation or a higher signal-to-noise measurement. It had a better model. A model that did not assume the orbit was circular before checking whether the orbit was circular. And when it removed that assumption, the data said something different from everything the previous analyses had said. The orbit was oval. The masses were wrong. The formation history was not what we thought. This is how science works at its most honest. The data has always been there. Sometimes the model catches up to it. We caught the ripple. We thought we understood it. We were reading it with an assumption we had never verified. 6 years later, someone checked. The orbit was all wrong, and in being all wrong, it told us something true. Good night.